Engineers found a way to trap a greenhouse gas inside solid rock permanently, and they are pouring it into sidewalks right now. Not stored in a tank, not buried underground waiting decades to leak, turned into stone forever. That sounds like the perfect climate solution. Take the gas warming the planet and turn it into the most widely used building material on Earth. But the real answer is far stranger than that, because not everyone agrees this is actually helping. To understand why, you first need to understand why concrete is such a problem in the first place. Concrete itself is not the issue. Cement is. Cement is the binding ingredient inside concrete, made by heating limestone to extreme temperatures in a kiln. That process releases enormous amounts of carbon dioxide, partly from the fuel burned to heat the kiln, and partly from a chemical reaction inside the limestone itself, called calcination, which releases CO2 as a direct byproduct. How much CO2 are we talking about? If the cement industry were a country, it would rank as the third largest carbon emitter on the planet, behind only China and the United States. Cement alone accounts for roughly 8% of all global emissions. So engineers asked an audacious question. What if you could take the very gas the industry produces and put it back into the product itself? This is called carbon mineralization. The science behind it is elegant. Concrete contains calcium compounds. When CO2 gas is injected into fresh concrete during mixing, it reacts chemically with that calcium and forms calcium carbonate, essentially limestone at the nanoscale. The carbon dioxide stops being a gas. It becomes a solid mineral locked permanently into the crystal structure of the concrete. Researchers estimate this mineral form can remain stable for hundreds of thousands of years. The carbon doesn't escape because it isn't being stored. It is chemically transformed into something else entirely. There are two main ways engineers do this. The first is CO2 mixing, injecting carbon dioxide directly into the concrete as it is being batched and mixed at the plant. The second is CO2 curing, exposing precast concrete elements to a CO2-rich atmosphere as they harden, instead of the conventional 28-day curing process using water and time. And here's the part that surprised even the engineers studying it. This process doesn't just sequester carbon. It can make the concrete stronger. The calcium carbonate crystals act as nucleation sites, helping the cement hydrate more efficiently and densifying the internal structure of the material. Companies like CarbonCure have already deployed this technology in more than 24 countries. Over 10 million truckloads of concrete have been produced using carbon mineralization. Producers using the system have achieved an average 4 to 5% reduction in cement content while keeping the same strength, translating into hundreds of thousands of metric tons of CO2 emissions avoided. That sounds like an unambiguous win. So why are some researchers raising concerns? The CO2 used in this process doesn't come from nowhere. It has to be captured from an industrial source, then compressed, transported, sometimes hundreds of kilometers, and finally vaporized and injected into the concrete. Every one of those steps consumes energy, and depending on where that energy comes from, it can release its own carbon emissions. A study published in Nature Communications took a much closer look at this entire chain, not just the carbon captured inside the concrete, but every emission produced getting it there. The researchers analyzed 99 published datasets on CO2 curing and mixing. Their finding was uncomfortable. In the majority of cases, between 56 and 68 out of 99 datasets, depending on the CO2 source, the full life cycle resulted in a net increase in carbon emissions, not a decrease. How is that possible if the gas itself is being locked into stone? Because transportation distance matters enormously. Because the energy required to vaporize and inject the CO2 isn't free. Because if the captured carbon comes from a source that itself runs on fossil fuels, you can end up spending more carbon capturing and moving the gas than you ever lock away inside the concrete. There's another factor buried in the data. When CO2 reacts with cement, It can sometimes interfere with the hydration process in ways that reduce the concrete's compressive strength. If a builder compensates for that lost strength by simply adding more cement back into the mix, the very ingredient responsible for the emissions in the first place, any net carbon benefit can vanish entirely. This is the trap of well-intentioned engineering. A solution can be scientifically real, chemically elegant, and still fail to deliver a net climate benefit once you account for the entire system around it, not just the moment the gas disappears into the stone. So does that mean carbon mineralization in concrete is a failure? Not necessarily. It means the location of the CO2 source matters enormously. Plants located near existing carbon capture infrastructure, where the gas doesn't need to travel far, and where the captured CO2 comes from a low-carbon process, show genuinely positive results. Plants relying on CO2 trucked in from distant, fossil fuel-heavy sources may not. This is why the next generation of research isn't just chemistry, it's logistics. Engineers and climate scientists are now mapping where carbon capture facilities, cement plants, and ready-mix concrete producers physically sit relative to each other. Because in this technology, geography can matter as much as chemistry. There's also a longer-term piece of this story that goes beyond mixing CO2 into fresh concrete. Old, demolished concrete, recycled aggregate from torn-down buildings, can also be exposed to CO2 and made to absorb carbon as it's reprocessed for reuse. Some researchers see this as an even more promising path, since it captures carbon while simultaneously solving the problem of construction waste. What makes this story so compelling isn't that engineers found a perfect answer, it's that they found something far more interesting. A technology that genuinely works at the level of chemistry, but only delivers its promise when the entire system around it is engineered with equal care. Somewhere in the world, a truck is still pouring that concrete right now. Whether the carbon inside it represents real progress or simply moved the emissions somewhere else depends entirely on decisions made long before the concrete ever reaches the truck. Thanks for watching. Like and subscribe to receive more civil engineering content.